Hello everyone, my name is Jason Molgaard. I'm a storage solutions architect at Arm, and I'm here with my colleague Eric Sondhi, who's a product manager for cycle models at Arm. And we're here to speak to you today about designing and benchmarking best-in-class real-time SoCs for storage devices. I'd like to begin by giving a quick overview of the Arm Cortex-R82. The Cortex-R82 is a recently released new processor from Arm. It's Arm's 64-bit Cortex-R real-time processor. It's a very high-performance real-time processor with 64-bit features to enable addressing very large memory address ranges. It has an optional MMU for running Linux and cloud-native software. And of course, along with that comes the Arm Linux ecosystem to enable a wide range of on-drive workloads. There's also optional Neon to accelerate machine learning workloads in a drive. The Cortex-R82 is, as I mentioned, a real-time processor with a classic Cortex-R architecture with TCMs, low latency ports. It is 64-bit, as I mentioned, with 40-bit physical address and that can address up to 1 terabyte of addressable space. There is an optional MMU to enable running Linux. So the core is capable of doing both real-time and running Linux. 256-bit wide buses allow for data to move in and out of the core very quickly. There's an integrated shared L2 cache between the cores, and it is optional to have coherency on the main master interface for the purpose of communicating with additional clusters of Cortex-R82 or other clusters of Arm Cortex-A processors in the same system. As I mentioned, there's low latency ports and optional Neon SIMD instructions for accelerating machine learning. So let's look a little bit more at the running Linux and real-time on the same processor. There's really two ways to go about doing this. So the first is that any particular core can run both at the same time. And the way this works is you would run a real-time hypervisor at the highest exception level, and then at the next lower level, you can have a virtual machine that's real-time and another virtual machine for Linux. If you're executing Linux and a real-time event occurs, the code can, via the hypervisor, switch out of Linux, jump to the real-time virtual machine, complete the real-time task, and then return to running Linux. So that's really interesting and provides a lot of flexibility and capability. I think that for a lot of the initial deployments, we're going to see people allocate the cores statically whenever they're integrating their system. So some cores will be allocated for real-time, some cores will be allocated for Linux. Either way, it enables a single controller to deploy multiple products. So for example, you could create one controller that in one configuration manages a very large SSD all in real time with the cores configured for real-time operation. That same controller could be configured for a different product where some of the cores are real-time to manage the FTL of the NAND, and the other cores are for running Linux for doing computation on the drive. This clearly reduces the number of very high-cost mask sets that need to be created. So a quick overview of some benchmark PPA data, as this is a frequently asked question. So we are getting up to 8.67 DMIPS per megahertz and 5.82 core marks per megahertz. We're able to run greater than 1.8 gigahertz in a 2 square millimeter area and 30 DMIPS per milliwatt. So pictorially, looking at some performance uplifts, we've got some benchmarks in gray and some user code in blue. I think that the user code is probably the more interesting since it's actual customer code that we've been able to simulate on the Cortex-R82 versus the Cortex-R8, and we're seeing almost a 2x performance improvement, and in some cases greater than a 2x performance improvement on actual customer code over the Cortex-R8. Looking at SpecInt, another industry benchmark, this is the same data presented in two different ways, both SpecInt and SpecFP for the Cortex-R82 relative to A55. And essentially, we're seeing a 21 to 23% performance uplift for the Cortex-R82 over A55. So with that background on the Cortex-R82, let's take a look at the next generation storage device applications. So one of the very hot topics that's getting a lot of attention in the industry these days is computational storage, where we want to unlock the value of data that's stored on a drive. And some of these drives are getting very large, 16, 32, 64 terabytes, lots of data on those drives. And we want to avoid moving all that data off of the drive to a host to do compute on it. So I've kind of selected 3 examples here that I'll kind of walk through briefly of how computational storage can really help improve the performance of a system. So first, taking a look at database acceleration. If you have a large database stored on a 16 terabyte drive, for example, and you need to move that entire database to a host in order to search for something in the database, that could take a very long time. High latency, a lot of bandwidth on the host interface to move that data. With computational storage, where we're doing the compute on the drive, we don't need to do that. We can just do the search right on the data that's stored on the drive without moving it. If you need to grow the database larger than the capacity of the drive and you add more drives, the compute naturally scales with it. You can get more compute with each drive that you add. No movement of those large files, like I mentioned. Low latency because you're not moving that data. And it helps with security because you're not moving unencrypted data across the host interface. You're only looking at it right there on the drive. So thinking about transportation, oftentimes a lot of data is collected and analyzed offline. A great example that I like is that commercial airliners that we all fly today store data on a drive, telemetry data of how the plane is performing and how the systems are functioning. When the drive reaches the gate, that drive is literally pulled out of the plane, taken somewhere, and uploaded to a server for analysis. It can take hours to days to not only upload but analyze that data, and the plane has long since left the gate on another flight before it's been fully analyzed, or even partially analyzed. With computational storage on the drive, that analysis can be happening as the plane is flying. And when it reaches the gate, the results can be known. Are there any anomalies that were detected on this plane and need to be reported or investigated? Video and image processing. Certainly content delivery networks are a very hot topic these days. With computational storage and having compute on the drive, we can efficiently transcode or encode video for streaming from the drive, or we can adapt to different bit rates for different resolution screens. And if you have a drive full of images, you can do image classification using ML right on the drive. So in order to take advantage of this capability, having a rich operating system run workloads on the drive is really the best way to go. In this diagram on the left, we're showing kind of a traditional SSD with 4 cores, 4 running real time to manage the FTL or the data movement on the drive, sending the data all back and forth to and from the host. On the right-hand side, we've got the same 4 cores, but we've reallocated a couple of them for running a rich OS like Linux, doing the compute on the drive and extracting the insight from the data instead of moving the data itself. With the Cortex-R82, we have the flexibility to change the balance of the workload dynamically. So maybe during peak times of the day, you've got a lot of data perhaps being ingested or read off of a drive, perhaps you need to allocate 3 out of the 4 cores for running real time and only 1 core for computational storage. Or perhaps you even need to use all 4 cores for running real time during those busy peak times. Later on, drive becomes less busy during off-peak times. We can reallocate some of the cores and use them for doing the compute that I mentioned. And so in this example, we've now allocated 3 cores for doing compute and 1 core for handling real-time management of the NAND in the drive. So using open source software is a great way to accelerate development for storage developers. So the ability to run Linux on the drive opens up a wide range of tools and technologies for developers that many developers are already quite familiar with. Combine that with the fact that all of the Linux distributions that are out there today are not only ported but optimized for ARM, including a lot of the applications. And so the familiarity with these tools and technologies is really going to make it easier for engineers to develop the code and deploy new solutions, innovate new concepts, and achieve time to market very quickly with new products. So looking at kind of an overview of a lot of the software vendors in the ecosystem, there's a number of them out there that have been ported and optimized for ARM. Certainly not going to explain all these, but I would like to touch on a few. Docker or Kubernetes or Rancher are great container tools to allow you to develop a workload on the drive, on your PC, and then download it to the drive and for execution. And if that workload needs to change, maybe today you're searching for images in a drive, and tomorrow you want to do something completely different, perhaps encode video, you just simply create a new workload and download it to the drive whenever you need to change the workload. So overall, ARM provides a full solution for faster development of a computational storage drive. So in addition to the processor IP, we have system IP, like interconnects and interrupt controllers. Perhaps for even more performant machine learning, maybe you want to have an MPU on the drive as well. In order to meet the power and performance targets, ARM offers physical IP to achieve the frequency targets and power that are needed for a successful computational storage drive. Very important is simulating up front with ARM Development Studio, fast models, cycle models, to do that co-simulation or code development with the software and the hardware, and look for system bottlenecks or opportunities to improve performance, benchmark, and really analyze the architecture of the hardware and the software together well in advance of actually not only taping out the design, but actually getting the silicon back. And this is a very important topic, and that's Eric will be talking about that here momentarily. And then finally, Cortex-R82 training and design reviews. We can help with any kind of reviews necessary to ensure that the design is on track and pointed in a good direction for success. All right, well, with that, I would like to turn it over to my colleague Eric so he can get into a lot more detail about the developer solutions available for the Cortex-R82.
Hi. Thank you, Jason. My name is Eric Sondhi, and I'm a product manager in ARM's Developer Solutions Group. I'm very pleased to be talking to you today about some of the developer solutions we have targeting both hardware and software developers to make your incorporation of the Cortex-R82 IP into your design a seamless, smooth, and rapid process to enable the innovation that Jason outlined earlier. So let's get started. I'm going to talk to you about a few different solutions for both hardware and software developers that range from a Cortex-R82 evaluation and just getting started to understand the Cortex-R82's performance relative to other ARM IP, and in the context of your workloads. As Jason mentioned, there's a range of capabilities with the Cortex-R82 in terms of hardware performance features, and there's a range of workload types that can be run, from sophisticated OS-guided workloads running in a hypervisor on top of Linux to real-time operations and timing critical code that you see in many storage devices today, to a combination of the two in a computational storage device working interactively. And so given that range of workloads and giving the range of performance uplift that can vary by workload, ARM provides an off-the-shelf evaluation solution that I'm very excited to tell you about shortly. In addition to that, we make sure to enable robust compiler support directly from ARM and supporting the earliest possible users with ARM architecture to the Linux environment and GNU toolchain to other ecosystem providers. And then beyond that, there's the technology that I look after as a product manager, but we provide as a complement to our IP to help our users develop, prototype with our IP very early, And we have comprehensive modeling support at different levels of abstraction for all use cases, ranging from the evaluation to performance analysis, SoC architecture, and early software development. And there's also an integration with that robust modeling support with a lot of our third-party ecosystem partners. Many of them are EDA companies, and there's integrations into their modeling environments, but also there are other workflows like emulation that I'll be able to go over with you today. So let's start with the IP evaluation use case. So what ARM has enabled directly to our partners is a simplified evaluation platform, which we call the IP selection sandbox. And this provides a very simple workflow to let users learn, evaluate, and select which IP and which configurations of that IP will work best and to start from. And this solution works out of the box. There's a graphical environment that allows you to select different core configurations, different IP, and instantly run simulations with example benchmarks, bare metal benchmarks that are included, or even import your own custom workloads or code snippets to run them on our IP and instantly analyze the IP with practical insights, comparing different IP configurations, comparing Cortex-R82 to an A55 as the benchmarking and graphs earlier did, or against other Cortex-R IPs, and to rapidly get insight. And those practical insights are very useful for rapidly getting a glimpse of how the Cortex-R82 performs across the configuration space for different workloads, whether machine learning code snippets enabled by the Neon hardware, or whether just different variations in the cache size and how they might even respond to basic memcopy type of operations. And also to do a core by core comparison as well. So you can select the different configurations you're interested in, queue up your simulations, run them, and instantly get feedback that's meaningful at a system level for the evaluation that you're looking at, and gives you the ability to drill down into top-level performance like cycle counts, but also hone in on marked areas of your code that are very timing sensitive and time those timing sensitive portions and get cycle counts for that. Right? So really understand how your algorithm performs on the IP. And then also, there's a lot of feedback you get at the system level, including basic bus info and numbers of reads and writes, max latency and throughput kind of information that gives you the starting point you need to have confidence in your R82 selection and the type of configuration you want to get started with. Now, we know that many users want to build prototypes that match their actual systems. They want to build software platforms that they can distribute to others, that they can start developing and porting Linux to, or their own device drivers to, or that they might want to iron out the I/O path, the CPU bus to memory I/O path and latency path, and they might want to build a more sophisticated virtual platform than what we might provide for an easy IP evaluation. And for that, we have a robust modeling offering that fits the overarching workflow that we see from our users. And that workflow consists of starting with ARM's compiler or other compilers from open source or third parties, right? And sweeping compiler options and generating different binaries with different parameters on the compiler, or different workloads or combinations of the two to generate those binaries. And usually those options are swept and the software is developed in conjunction with the virtual platform, right? And you start to bring up your software on a virtual platform comprising of fast models. And we have that phase for developing and debugging code at instruction level or source level to make sure you can build binaries targeting the Cortex-R82 and related components that you have in your system, and then simulate that platform on a cycle-accurate equivalent. And through that process, that gets you to analysis, and that lets you visually correlate the hardware execution against the software execution and match PMU events and cache hits and misses alongside the lines of source code that we're executing at that time. And that lets you debug complex timing issues with full visibility and cycle-accurate granularity. And that overarching analysis, that unified hardware and software analysis, is what our partners and many of our hardware and software developers need to holistically validate the compiler options in their binary that make the most use of the Cortex-R82 hardware, and also validate the software's execution and validate their architectural design decisions at the SoC level. And in order to do this, so we start with the robust compiler offering that ARM offers through our partners indirectly. So directly, we have ARM Compiler 6 with the earliest architecture support and some of that performance uplift that Jason was referencing earlier. And there's continuous work done to optimize the compiler to balance code size against performance to help our partners get the most out of the Cortex-R82. There is robust GNU toolchain support for booting Linux on 64-bit Cortex-R. And we've also seen an uplift, performance uplift over not just R series, but A series running spec on Linux with the GNU toolchain, which is freely available from the ecosystem and enabled by ARM with community support. And then there are also our partners in the ecosystem like Greenhill Software that can enable step change core mark performance on standard benchmarks. And they're a prime example of the role the ecosystem plays for enabling our partners with the latest and greatest ARM IP, no less. Okay, so with the compiler support that we also have very robust modeling support. And this is where I look after the ARM cycle models, which are at the lower left end of this spectrum. This is a continuum of simulation speed on the y-axis and abstraction on the x-axis. So on the lower left, we have cycle models, which are 100% cycle accurate, very detailed, provide a RTL accurate representation of the Cortex-R82 for benchmarking, driver development, SoC architecture, and they're actually running under the hood of our evaluation platform. And these components are very useful for building out that accurate platform. And then at the other end, we have very fast, high-speed, abstract programmer's view level ARM fast models. And with the fast models of the Cortex-R82, you can start that work of incorporating Linux and a lot of those third-party Linux-enabled ecosystem software components into a hypervisor that partitions your Cortex-R82 into a combination of real-time RTOS guided workloads working alongside that Linux host doing the insightful calculations and computations on the data that's proximal. So that's a modeling core technology under the hood that enable both the software developer and the SoC designer. And we also have offerings that trade off speed and accuracy, whether by adding timing annotation to the fast model or by integrations with our third-party EDA partners, like enabling the modeling environments to mix and match fast and cycle models in a pure virtual hybrid, or for bringing fast models into an emulation environment to run co-emulation to run fast or run accurate. And I'll talk a little bit about that shortly. Our models are available in a flexible simulation environment. They are fundamentally available in System C, an open source platform that allows our partners to bring in their own System C models, and we support timing accurate to loosely timed TLM modeling interfaces to help our partners stitch together these ARM fast model and cycle models into systems. And there's some utility components for those users that use System C natively. But then we also have very full-featured integrations for both fast models in the Synopsys virtualizer environment and cycle models in the Platform Architect environment from Synopsys. And actually in Platform Architect, we have the ability to mix and match the fast and cycle models into virtual hybrids to balance simulation speed and accuracy, and to bring in your own abstract components or very detailed components. And that makes for a very unified hardware and software debug and analysis platform. And the integration with Synopsys really allows our modeling capabilities to span our users' use cases from the specification side to early software development, where you're bringing in abstract, loosely timed models, taking advantage of the library of ARM fast models, including Cortex-R82, into a graphical modeling environment and building virtual platforms for software developers to use. that are based on your design. And that moves forward into the hardware-software optimization validation that you can enable in Platform Architect when you bring in cycle-accurate models, ARM cycle models, to add accuracy and further refine your virtual platform for doing more detailed analysis and moving our hardware developers closer towards implementation. Okay, and this environment is it's enabled by a really robust integration and tool offering that includes a platform creation tooling suite that's completely graphical, that has both of these ARM and fast model and cycle models included in the library and able to use, along with TLM Creator to bring in your own models, and also import your own System C models into a very powerful platform creation suite that can also be used in co-simulation and co-emulation. And run System C simulations, connect to ARMDS and debuggers, extract really rich information from the modeling platform so that you can analyze software at source level, at instruction level, even at transaction level, analyze that software execution and compare visually correlate the hardware events that are taking place when that software is executing, and really get a depth of analysis, simulation control, and debug capability that's really paramount when you're looking at hard, real-time, timing-critical hardware and software interactions. So that offering and also the co-emulation that this platform also enables, that is also extended. And we know that many of our users take designs beyond their virtual platform into prototypes that are fully accurate, right? And we know many partners like to move beyond fully virtual platforms and start to take their SoC design phase into an area that's closer to system validation, verification, and an SoC hardening. And for that, we partnered with many of our EDA design partners to enable co-emulation with the fast models. And the next example is the result of a partnership we have with Mentor Graphics. And we've enabled a really scalable modular storage controller verification environment where on the left here you can see a guest OS running iometer or any other stimulus into a virtual lab environment, which is based on a Veloce emulator that has what's called HiCon technology for the host processor, and this could be the Linux application processor running on the Cortex-R82 core, paired up through a PHY to a customer's storage device, and this could be another core on that same Cortex-R82 running the real-time host processor. And here you can have a basically full implementation complete design that can run iometer of your storage controller, and you can run fast, running HiCon and the Linux kernel from a fast model, or you can run completely accurate with your whole R82 design under test in that SoC or SSD controller SoC space. So there's a lot of flexibility and a lot of visibility, debug, waveform analysis that this platform can enable out of the box. And it also gets you 95% performance correlation with silicon in the storage space. So it's really exciting capability that our partners have enabled. So with that, I'd like to just provide a brief summary here that we've sharing with you the Cortex-R82, which accelerates the next revolution in data storage. This is a brand new 64-bit Cortex-R CPU that can run Linux capable. So greater performance, MMU capabilities that Jason laid out, very flexible. One storage controller design can tape out a traditional SSD or a computational storage device. And you could even dynamically manage the cores and how they run based on workloads over time. And this technology accelerates innovation and coupled with the overall solution, whether the physical implementation, system IP, the training, or the developer solutions, enables our partners to rapidly adopt this IP, take advantage of the rich operating system and ecosystem-enabled software ecosystem that goes along with it, to start running cloud-native software and speed up your development and time to market. And we'd invite you to get started today. Get started with your Cortex-R82 evaluation today by contacting myself or Jason or Neil Werdmuller, the storage director here at ARM. And with that, I'd like to thank you all for your time and attendance today. We look forward to working with you and adopting Cortex-R82 soon.